It's a great pleasure to host Chiara Petrone today. She's here thanks to she's the distinguished lecturer of the Mineralogical Society of the UK and Ireland. She's one of the two for this year, so thanks a lot for coming to Geneva as well. So she will speak today about petrological monitoring of active volcanoes, one crystal at a time. So this is my interpretation of what you do for a living. So Chiara is a leading international colleague working at the interface of petrology and volcanology and advancing the field of petrological monitoring and especially diffusion geochronology. She's an expert of using diffusion profile of minerals to reconstruct timescales of processes. All of this is essential to determine the evolution of ongoing eruption. These were things that now start to be applied, for example, to understand when La Palma eruption will have ended. That was one of the questions, for example, in that case. And to use the eruptive history of volcanoes for hazard management. So this is becoming really one of the functions of volcanology. Before we were only doing post-mortem stuff. Now we are actually in the center of attention also for this. So she's a merit researcher in volcanology and petrology at the Natural History Museum in London, a visiting professor at Imperial College, and she's the co-editor-in-chief of Earth and Planetary Science Letters. Vice president of the Science Committee of Geological Society of London. She got the PhD and so you did the master and the PhD. The PhD, I think she finished 5 years ago at the University of Triana. So she's an early career scientist. The University of Florence in Italy. Then you did a postdoc. Oh, but I didn't know that. Postdoctoral fellowship at the University of Kyoto and at the Carnegie Institutions of Washington in the US. She had various projects, and one of these was erupt in the EU, and you helped setting up the laboratory of geochemistry in Florence, I understand.
Yeah, long ago.
6 years ago. She's an expert of microbes. She uses a lot, so she has a little visit on our lab, and we hope we can do some collaboration together. And I think I leave it here. We are really happy to have you, Chiara, so please.
Thank you. Thank you, Luca. Thank you, Chiara. And thank you, everybody, for coming today and for inviting me. I'm very excited. And I hope to do justice to the work that, as a community in the petrology, we are all doing in terms of trying to bring really the petrology into the action of monitoring volcanoes. So, okay. Yes. Okay. So I think we all have a good idea how volcano monitoring works, with a lot of instruments deployed on a volcano trying to capture all the signal, gas, deformation, seismic, and so and so. But clearly, a volcano is a very complex system with a plumbing system that extends down the volcano in what we now call the transcrustal magmatic system. And so the magmatic processes that then drive the eruption and prime the eruption start somewhere there. And so it's quite important to understand what is happening there. And clearly, as Luca said, this information can be unlocked via petrology, but for a very long time, petrology has been an a posteriori or post-mortem tool, so not very useful for volcano monitoring. But we are definitely getting better, and in the recent year, we have seen the deploy of petrology to really understand as a near real-time tool, near real-time because we still need the eruption to occur, then we need to collect the rock and analyze the rock. But the overall, the analytical capability is really improving a lot. And in this study from Corsaro and Miraglia, they basically look at they analyze the glass of Mount Etna during the eruptive period between December 2020 and April 2021, basically in real time. And what they saw is the changing in the signature of the glass getting more mafic until the 28th of February. Sorry, so if I point here, maybe everybody can see, 28th of February, and then going back to where it was. So clearly a very useful tool during the eruption to understand the evolution of the plumbing system. Similarly, and Luca mentioned this, is the excellent work done by Matt Pancras and co-author during the volcanic eruption in La Palma in 2021. Basically, they collected the rock on a daily basis, and they start to analyze with very fast analysis of mineralogical phase in this mineralogical map to target some interesting mineral, and then going to analyze in more detail with electron microprobe. Basically, within 10 days from the collection of rock, so from the eruption to doing all this analysis, they were able to provide some information, key information during the eruption. And so this is really all good. And actually, they in the paper, they say that the rapid response of petrology can really untangle complex magmatic processes. But the problem still is how we link these processes with the monitoring data. So clearly we can do during the eruption with fast analysis, but the other key point is to have a timeline of event, of the petrology event, to link with the timeline of the monitoring data. And so the key is clearly in the mineral, nothing new here. Mineral that record the changing in composition. This is a nice zoned pyroxene from Stromboli, where we can see the chromium changing from the core with high chromium, then the low chromium in the mantle, and then high chromium in the rim. So clearly the chromium in this case is linked to a more mafic composition, and telling us how the chemistry of the magma changed during the life of this crystal. We know that, and all the work that Luca is doing to retrieve the pressure and temperature and get a better idea of the configuration of the plumbing system. But the other key information that is locked in the mineral is the time information. So when this process occur. And in this sense, sorry, I don't know why it's not working. Okay, so in this sense, what sort of processes and what sort of time scale we are looking? So we have two ways to retrieve the time of the mineral. One is the radiometric dating, here in red, which basically are based on the decay of element, radiogenic element that decay at constant rate. And so they allow to give an absolute age of the mineral. But we can see that this span from 1 million years to maybe century. And then the other tool, which is a more flexible tool, is the diffusion chronometry tool. Here, all the possible combination of diffusion chronometry in blue, which span a very large range of time scale from millennia to hours and minutes, which is very relevant for the different magmatic processes that we can see in the upper part of the where all the green tell us the duration of different processes from the assembly of large volume of magma, which can range in the time of million years to millennia, to crystal entrainment and growth, which are on much shorter time scale until the eruption. So going back to diffusion chronometry, basically here we can see a list of mineral and some elements. So diffusion chronometry is based on the diffusion of the movement of element from one side to the other of the compositional boundary in zoned crystal. And we can see that each of these pair of elements, a mineral, they have a window of applicability, which depend on how fast the element move, on the crystallographic characteristic of the mineral and other parameters that we explain in a minute. So, for example, if we look at the diffusion of magnesium in plagioclase, we can determine time scale, or we can target time scale from century to months and days. But if we are concerned with much shorter time scale in the term of minutes to hours, so really the pre-eruptive, or the few minutes to a few hours before eruption, we need to look at the lithium in plagioclase, which move or diffuse at a very fast rate. Okay, so how do we start this diffusion chronometry clock? Well, clearly we need a disequilibrium within the mineral, so we need a zoned crystal, which can be formed because a new magma arrives, or changing in pressure, temperature, a combination of this process. Once the diffusion, the zoned mineral is formed, and we have this compositional boundary, if we imagine to measure the composition of this crystal from the core to the rim, basically while it's forming, we will have a very sharp compositional boundary, exemplified here by this dashed gray line. So as soon as this compositional boundary forms in this equilibrium, so elements start to move from one side to the other of the boundary, they tend to retrieve the equilibrium. And so this movement is function of what? For the element, if they move fast or slower, as we have seen for lithium, example, lithium and magnesium in plagioclase. It's also a function of the type of crystal, but the other two main parameters, one is the temperature, so the higher the temperature, the faster is the movement, and the time. The longer the time spent, these crystals spend at the magmatic temperature, the longer with the movement, or the element can move much longer. So what is happening is that this very sharp initial compositional profile start to smooth, and this smoothing is function of temperature and time, and is controlled by the diffusion equation. I'm not going into any detail, but the main point is that we can resolve this diffusion equation for time, and it's also dependent on temperature. So if we know the time and the temperature, we can resolve this diffusion equation. One main point is that the diffusion only happens at the as long as the crystal is in the magmatic environment. So it only happens at the high temperature of the magma. When the eruption occurs, the diffusion stops, and the smoothing of the profile will freeze. And so we can measure the smoothing of this profile, the red dot there, and applying the diffusion equation, we can retrieve this relative time. So how long before the eruption this event that formed the compositional boundary occurred. Okay, so, and this is really good, and there have been a lot of study looking at the several of these time scale. One of the main process they have target is the time scale of magma mixing to eruption, because it's one of the main process priming an eruption. And this is a compilation from Fidel Costa in 2020 of several volcanoes, from basaltic one in blue to silicic in red, with time scale ranging from days to millennia. And we can see that these time scale are system dependent. Silicic system, they retrieve, they indicate time scale much longer than the basaltic system. But one of the points of this study is that the magma mixing to eruption is one of the processes that is really telling us about the last or one of the last process recorded by the mineral, and usually occurring in the shallow system prior to eruption. And so it's the last process recorded by this mineral prior to eruption, which usually is recorded by the rim. And this is a really important information, because we can try to correlate this time scale recorded by the rim with the monitoring data. As a sample that we did for Colima volcano, And this is the part of the PhD student, the PhD of one of my former students, Gerard Hughes, that we published last year. So Gerard looked at the period of activity of Colima volcano in central Mexico, big stratovolcano, quite eruptive, quite active. Look at the activity from 2013 to 2017, and particularly focused on the pyroxene, the orthopyroxene, the reversible zone orthopyroxene that we can see there, with a low magnesium core in light gray and the high magnesium rim in dark gray. So, and looking at the time scale of this, the moment the mafic rim formed by the arrival of the mafic recharge. So these are the time scale for this different period. They range from about 2 years to less than a month. And the good thing is that since we know when this rock erupted, we can transform this relative time scale into absolute time, okay? And we can get a timeline of events for each phase, as reported here by this density curve. And so we can see that we have a clustering of this, the clustering of the individual time scale for individual crystal. They allow us to recognize an event of mafic recharge, signal here in, sorry, I always forget that there is signal here, indicated here with this double arrow. So this is an event of mafic recharge in phase 2 that occurred about 180 days prior to eruption, and the eruption is this red rectangle here. In other case, we have more than one mafic recharge prior to eruption, like in phase 3 and 4. The first one in phase 3, we have one mafic recharge about 10 months prior to eruption. Then a second one, 4 months prior to eruption. And finally, a cluster, the last cluster of time scale indicated a mafic recharge just less than a month prior to eruption, so triggering the eruption. So we have a priming phase and then the triggering. The other interesting thing that we can see from comparing, for example, phase 3 and phase 4 is that some of these mixing period, they coincide, they are the same mixing period. So this means that the mafic recharge arrived in the system and was recorded by several crystals. Some of these were erupted during phase 3 and others remain in the system, were erupted in the subsequent eruption. So if we put everything together for this different, for all the period in this density curve here at the bottom from the 2013 to 2017, I apologize for the busy slide, but hopefully I can make sense of this in a minute. So we have all this mixing period, and we could identify 3 large mixing periods. This one, the first one in blue, then the orangey one, and the green one. And we compared this timeline of the petrology data, so the mixing, the magma mixing, with the several monitoring data. So the SO2 flux here, the tremor duration, the seismic signal, the LP, the explosion, and the rock fall. So in some case, like in mixing period 1, we don't really have any correlation between the petrology and the monitoring data. And this can be due to several reasons. One reason is possibly because we have a very low frequency of magmatic injection, which is not really detected by the, or low volume, we don't really know, but it's not detected by the monitoring data. And this is a bit disappointing. But if we look at the high frequency period, like period 2 and period 3, then we have a good correlation with the monitoring data. And in particular, we can see that when the mafic recharge arrives, then there is an increasing in SO2 flux and increasing in seismicity and so on. So this means that basically when we have the mafic recharge, this is clearly, this mafic magma is also accompanied by gas. The gas then starts to degas and ascend, and giving the ascent into the conduit, releasing gas, which is picked by the monitoring data, and also seismicity. Then a new mafic recharge arrives, and this process repeats itself until the last mafic recharge triggered the eruption. So, and we have seen this sort of study, there are more and more of this study. Actually, Katie Chamberlain just published one on La Palma, which is really a very interesting and very good study on all the data that they collected during the eruption, but clearly the time scale are very time consuming, and so it was impossible for them to do on near real time. But these are very useful to interpret the monitoring data. However, these are the information that we can get from the rim, but not all the crystals are so simply zoned with the core and the rim. Most of the crystals, they have complex zoning, like something this one with multiple bands, multiple events. So they record in their lifetime multiple events. So if we consider the crystal as a sort of analog with a tree trunk, is kind of trying to get the and infer the life of the tree only looking at the last ring of the tree trunk. Instead, in the last, well, now 15 years or so, we have, as a community, we have been really trying to get inside the crystal and resolve multiple compositional boundary. So to reconstruct a sort of elemental diffusion chronostratigraphy, if we would like to give a name. Anyhow, all this started with the brilliant work of Maren Kahl on the olivine of Etna, where she basically looked at the olivine zonation pattern Etna volcano, and using this system analysis, from she was able to reconstruct the movement of each olivine from one magmatic environment to the other, and also the time scale. Clearly, each magmatic environment has a different temperature, and so soon after, Tim Druitt, a collaborator working on plagioclase on Santorini, they tried to apply to consider this. They considered this changing in temperature for a crystal, for a plagioclase, which has an inner core, this red one, the core, the orangey one, with the different temperatures, so the fresh compositional boundary between the core and the inner core and the core, and then a final rim with a different temperature. And so what they did, the first model, both compositional boundary, the inner core and core, so the internal and the external and the core and rim, at a single temperature, at the temperature of the final rim. And we can see that the match between the measured profile, the open circle, and the model diffusion, the red one, is not really great. And then they applied two-step model, first model in the internal boundary at one temperature, and then the rim at another temperature, and they got a definitely better match. So starting from this and considering these few years after that work with my colleague, we proposed this approach to diffusion that we call a NIDIS, non-isothermal diffusion incremental step model, where we consider the fact that each layer or each part of the crystal has a different temperature, and also that when the internal boundary is isolated from the melt by the overgrowth of the rim or a further external layer, the diffusion inside in the internal boundary does not stop, but will continue until the eruption, but at a different temperature, the temperature of the rim. So we try to embed the variation in temperature for each layer. And basically, we used a backward approach, starting from the rim, deconstructing the complex profile in single isothermal step, and each one considering the temperature. And in this way, we were able to determine the time scale of crystal storage in the different magmatic environment, but also, for example, the duration of the magma mixing, resolve the multiple mafic injection, or resolving the time scale of remobilization of anticrystal core, like this resorbed mafic core. Okay, so now for the rest of the remaining of the talk, I would like to show what sort of information we can get when we combine the information from the rim, the information from the inside, the internal part of the crystal, and using a multi-mineral elements approach a multi tool approach. So not just looking at the time scale, but also, for example, the variation in strontium isotope composition. So I take you on Stromboli volcano. Look, already recognized this. And to really look at what we can get in terms of inference from the longevity of the plumbing system. So Stromboli volcano in southern Italy, I think, is well known, but just to give a very short recap, is well known for the Strombolian activity, this explosion that's occur at very a short interval, about 20 minutes or so. From time to time, this Strombolian activity is interrupted by some major explosion called major Strombolian, call it major eruption, and for every few years there is some larger explosion of very short duration but very powerful, call it paroxysm. So the normal Strombolian activity and most of the major explosions are fed by this degassed high porphyritic magma here at shallow level, 3 kilometers, call it HP or high porphyritic magma. But we also know that there is a deep-seated magma here, the red one, which is volatile rich and crystal pure, the low porphyritic LP magma, which is only erupted during the paroxysm as a single magma. But the continuous arrival of the low porphyritic magma into the shallow magma is what sustained the activity at Stromboli. So regarding the paroxysm are kind of rare event. It was one in 2003, one in 2007. But in the summer 2019, there was a very unusual sequence of events. Started with on 25th of June with a major eruption, and then two paroxysms, one on 3rd of July and the other one 28th of August. So within a very short time, 64 days, two paroxysms. And of course, I mean, everybody was curious to know why this happened. And with my colleague, we started to look first at the pyroxene, the decline of pyroxene and Stromboli, for these three events of the summer 2019. In terms of composition, the 2019 clinopyroxene are exactly the same as the rest of the present-day activity of Stromboli, with a low magnesium composition here, the light gray augitic composition with Mg number ranging between 70 and 80. And then there is another composition, which is the diopsidic one, the dark gray, which is with magnesium number between 80 and 19, so a more mafic magma. The augitic one are in equilibrium with the shallow magma, whereas the diopsidic composition are in equilibrium with the more mafic and gas-rich magma at deeper level. In terms of texture, the texture are pretty much the same as observed in the previous activity, in the present day activity, but the frequency of these texture are quite different in the 2019 sample. So we have a group 1 characterized by the low magnesium, the augitic core, that can be homogeneous or slightly zoned, as in subgroup 1A, or they are clearly marked by a well-defined diopsidic rim, as in subgroup 1B. Then there is a group 2 characterized by diopsidic core, which again can be homogeneous or slightly zoned, as in subgroup 2A, or they can have like a resorbed core surrounded by a extended augitic overgrowth. The subgroup 1B is very frequent in 2019, was not so in the previous period that we analyzed, for example, between 2003 and 2017, which I will talk later. This other group, the group 2B, is not very well represented in 2019, but was more frequent in the previous period. So in terms of, if we look at some compositional map for trace elements like chromium and nickel for this different group, if we look at the diopsidic composition of group 2 and the rim of group 1A, we can see that chromium and nickel go hand in hand, really signaling the arrival of mafic recharge or more mafic magma. So in one case, this rim, they really testify the arrival of the deep-seated magma into the shallow reservoir. Whereas for the group 2, they signal the crystallization in equilibrium with the deeper magma. And in particular, this resorbed core of group 2b, they are interpreted as anticrystal from remobilized from the crystal mass. The augitic composition of group 1a and the overgrowth of group 2b are quite interesting because, yes, they are in equilibrium with the shallow magma. But if we look at the overgrowth of this, the group 1a and 2b, we can see this very finely zonation in chromium, concentric zonation in chromium, which does not correspond with the nickel, So this means that the chromium in this case is controlled kinetically by a growth of this crystal in a very dynamic environment characterized by convective stirring. Okay, so in terms of time scale, come on. Okay. In terms of time scale, red one are all the time scale for the 2019. The gray one are the time scale that we measured in a previous study, the Stefan et al. 2020, from 2003 to 2017. And I talk about this later. So let's focus on the red one. They range from a few years to less than a month. And the majority of the short time scale belong to the to the rim. And they probably signal the triggering of the eruption. So let's focus a bit more on this short time scale. First, the rim, the diopsidic rim of this crystal, which are only found in the 2 paroxysms. There are no crystal like this in the major eruption. And they have really short time scale from few months up to a few days prior to eruption. So really indicating the arrival of mafic recharge, the big role played in this case by the deeper reservoir in triggering the eruption, both paroxysms. And this is also confirmed by the time scale of the diopsidic crystal, the 2A, which they completely overlap with the triggering, with the rim, and they are not found in the major eruption. And they really indicate that these crystals were brought by the mafic recharge into the shallow system and had really no time to interact with the shallow magma. If we look at the time scale of this crazy oscillatory rim, they mostly overlap with the mafic recharge. They also find the major events, so they expand, they are slightly longer, but suggesting that the arrival of the mafic magma is what really enhanced the convective steering of the shallow reservoir. So this sort of time scale have some implication in terms of interpreting the change in eruptive style as stromboli. So we can transform this time scale again in a timeline of events here at the bottom of this diagram. Okay, so we can see that we have a mafic recharge starting, a continuous mafic recharge, which is the basic, the normal activity at stromboli. But then starting in June 2019, we really start to see an increasing of mafic recharge, culminating with the first paroxysm on 3rd of June, and then a second event of mafic recharge triggered the second paroxysm. So if we compare this with the gas data from IUPA, the increasing in gas data and the explosivity from the work of Andronico, 2021, we can see that there is a very good correspondence. So there is an increase in gas, an increase in explosivity, and the arrival of mafic recharge. So this basically means that the gas and the magma remained coupled for the entire period, and both paroxysms, they were triggered by a bottom-up mechanism. So now we know the mechanism, but how about the reason why we have 2 paroxysms? So the answer lies with this guy here. So the remobilization of this anticrystal core from the crystal mass that return time scale, longer time scale. For the 2019, we're talking about 5-6 years. So whatever immobilized this crystal has nothing to do with the triggering of the 2019. And if we look at the time scale from the previous period of this crystal from the previous period, so 2003 to 2017, the gray one, we can see that some of these crystals were remobilized 100 years before being erupted. And so in 2020, in the work of Di Stefano, what we proposed, so in this first panel and the panel A, what we proposed is that between 2003 and 2017, there was an extensive interaction between the LP magma and the MASH, with an extensive remobilization of this MASH, which now we propose that continued until 2019, leaving a rejuvenated system with almost direct link between the shallow reservoir and the deeper reservoir, and almost an immediate response to the arrival of the mafic magma. And this is also linked to a higher variability in eruptive style. And there was another, and it also probably linked to the fact that there was another paroxysm in 2024. Okay, so this is this is for the MASH that we see here. But how about the shallow reservoir? What is the role of the shallow reservoir? To explore this, we look at the plagioclase, from the work of Beatrice Schiavone, another former PhD student. And we look at the plagioclase from 2003 to 2021. They look like this, with the anorthite rich core, then an anorthite poor band, another band anorthite rich, and finally an anorthite poor core. In this case, we first determined the strontium isotope composition in some portion of this plagioclase and also the pyroxene. And here they are, in green the plagioclase, and in orange the strontium isotope composition of the pyroxene. And we can see from 2003 to 2013, we do have all the crystal plagioclase and clinopyroxene indicate a low strontium isotope composition, which is very similar to the strontium isotope composition of the present day activity of stromboli from mineral and whole rock, as from literature data. But starting from 2017, we start to see a high radiogenic group here, which we haven't seen in the present day activity so far. And in fact, we need to go back to the neostromboli period, 13.6 kiloyear ago, to find the same strontium radiogenic signal. And so, since there are no evidence that there is a change in the magma source, and these are isotopes from portion of the crystal, from core and from some of the band, so the only explanation, or the most plausible explanation, is that this, starting from 2017, the remobilization of the MASH was so extensive that an older unseen MASH started to be remobilized alongside with some interstitial melt or antemelt. So if we look at the time scale of this remobilization, in particular the magnesium diffusion in plagioclase, we calculated the remobilization of this MASH for all the period, and compare with the strontium isotope signal and with the gas data from IUPA. Particularly starting from 2017, there is a very good correspondence between the increasing in strontium isotope composition, increasing in gas, and the frequency of the mafic recharge, which really indicates that we have this extensive remobilization and cannibalization of the MASH. And this has really important implication in terms of the longevity of the system. We can see that the system may persist really long, basaltic system may persist really long, up to 10,000 years, which so far we really thought that the basaltic system were very short living. Okay, so just some take-home message. I hope that I convinced you that the diffusion chronostratigraphy is really powerful to understand the magma dynamic. And as a community, we really need to devise a high frequency petrological monitoring tool, because this is the future, and basically because we can get way more information. And the other thing is that to combine multi-mineral and multidisciplinary approaches, above all, a more collaboration among different groups. So clearly, I'm standing here, but I'm indebted to lots of collaborators, and particularly to my student, former present student, and I stop here. Thank you very much.
I have 75 questions, but yeah.
We can talk later.
So it's really nice. It's a relative timing. I wonder how we can do absolute timing. Is there any way we can use different size, and then use it to get absolute timing?
Yeah, I suppose that's the next step. There are work that they not only look at the time scale, but they're trying to embed the growth rate to the time scale. So there are some model like Mooch, Mooch is trying to embed, Peter Costa is trying to embed the growth rate. Yeah, that's the next step.
Then you can really pinpoint the event and the duration.
Yes, yes. But yeah, one of the, so there are two main points. One is trying to really understand the growth rate and what is the role of the growth rate. At the moment, we assume that the growth of these different boundaries almost instantaneous. And the other way is to look at the slow diffusing element if they still preserve their diffusion or the initial composition to kind of exclude the growth. But this is a big assumption. So one is that to really embed the growth rate and understand the growth rate for the different mineral. And the other one is the error on the temperature, which is a big factor. Well, of course, then there is the error on the diffusion coefficient and so on. But I think if we can resolve at least these two, yeah, that would be the next step, definitely.
Thank you very much. I have a question about your modeling of these diffusion profiles. So in the diffusion profiles in your models, you're trying to fit both temperature and duration. Right, so for a certain set of diffusion parameters from Cherniak or something like that, you're fitting the amount of time it would take to get that profile at a certain temperature. So in your models, you're seeking two variables, right?
Yes.
You're not assuming temperature, you're also getting temperature from the model, the best estimate from the model.
I get temperature from thermobarometer and then I input the temperature.
Right. So
and then with the temperature, I calculate the diffusion coefficient.
Right.
And then, so the model is only to fit the time, basically.
Right.
It's a fitting model only for the time, assuming that the temperature is correct and the diffusion coefficient is
So
correct.
you're just doing forward models then? You're just doing simple forward models, or are you doing
For each step is a forward model. But then when I apply to different boundary is a backward. So basically, I first calculate the time scale for the ring.
Right.
And then I know how, basically, how smooth is that curve. And that parameter I applied when I go inside. I say, okay, my initial profile, so I start from, even in the inside, I start from a very sharp profile, but then I know that a part of that diffusion, a part of that smoothness is due to the fact that it was at the same time of the ring.
Right.
Okay, so, and I know I can apply that and I can consider this my new initial condition to fit the real.
Okay, I'm quite curious how you're dealing with well, actually, are you only really interested in the intra-grain variation in concentration away from the boundary? Or are you also interested in the boundary? And if you are, how are you treating the grain boundary as an open system to an infinite reservoir?
Yes.
Yeah,
okay. I mean, yes, if
risky.
Yes, it is. So for the rim, basically, it's kind of an infinite reservoir, assuming that there is equilibrium. Then when you move inside, it is a limited reservoir because.
Are you assuming, sorry to ask too many things, I should have.
No, that's fine.
Are you assuming that the exterior then is just melt? That's why it's an infinite reservoir?
Yes.
Okay, all right, fair enough.
Yeah.
Because we did experiments, well, numerical experiments, not real experiments, with diffusion of lead and apatite, and the boundary condition is critical.
Yes.
If it is semi-closed, then the temperatures required would go up by hundreds of degrees for a certain amount of lead loss in the boundary.
Yeah, there are
The
some.
boundary condition is really does control how you would model, what the outcome of those models, I would suspect.
Yeah, the assumption is that since these are so you have the crystal and then you have the melt, so they are porphyritic basically. So you have an infinite melt and they have time, the rim has time to equilibrate. But of course, when you start to look at the interior of the crystal, at some point you have a finite reservoir because it's confined.
I sneak in one.
Yes.
So I think it's very interesting what you show with the isotopes, for example, of stromboli, because so to cut it short, do you think this is the beginning of a different period of activity for stromboli?
Yes. to keep it short, but yes. And I think we have indication that there's a different period of activity. I mean, starting with 2019, but also probably with 2017, we can see that there is a more energetic activity. We have way more and more major explosion than there was in the past. Everything is quite different, actually.
Because you work in the past as well. So you say 13,000 years, you start to see the same strontium isotopic composition.
Yeah.
I don't remember, did you work more back in time? Or do you see any cyclicity of these periods of?
Yes and no. So in terms of the texture of the crystal, it's quite interesting. So not the texture, the frequency of the different. Yes, I can see some cyclicity. Also in terms of time scale, actually, I wanted to show, but I still like very. I can show you later.
Yep.
But yes, there are some correspondence with the past activity that is more similar to what is happening now. I don't have data that show, I mean, basically the period between 2003 and 2017 to compare with the past, but I have data that showed me that actually what we've seen since 2019 is similar to the past. So, yeah.
I mean, Stromboli, this is a big issue because it's a very touristic volcano.
Yeah.
Before the 2019 eruption, there were 500 people waiting to go up.
Yes.
They would have gone up, they would have died, and there was no sign that something was about to happen.
No.
So obviously that's a bit of an issue.
Yeah, no, they had some, well, I mean, with inside they see that there were some, now they can see there were some signal, but at the time they had only 10 minutes. 10 minutes before they realized that something was going on. And by the time they realized something was going on, it already happened. They said, oh, that's it. Yeah.
Yeah, so it's.
Yeah, I mean, this is a very nice question. So you have now you're making the step from pre-mortem to sin-mortem technology, but actually we go the step further to the post to pre-mortem. There's something more about, of course, temperature, magma mixing, all this plays a role, but I think then the dominant factor becomes the volatiles, or am I wrong? So
Yes.
you have then to make the step to also reconstruct the volatile state. Back to the pre-mortem.
You need to restart another PhD. Yeah.
Yes. I need some students that will on that. No, I mean the volatility and how we need the volatile with all this, because I mean, yes, when you read the time scale, you can see that they kind of talk to each other, but there is still this big question on how much they really talk to each other in the sense. So one point is that we really have some big uncertainty in the time scale. So what we see, we cannot really match precisely with the data, the monitoring data, the timeline. And also, I mean, yes, so if you have magma, clearly you have an increase in volatile. But what is the role of that volatile in the time scale? Yeah.
If I may reach up on this, you have a nice picture where you show the increase of the LPs with the transit as well. So I actually wonder whether you have something that goes through the, I don't know, like the geologically ductile shoulders of your system. So you have these pressure fronts that are traveling, or is advection of magma when you relate it to the volatiles? Because, you know, this is something I really never kind of figure out. How much is a pressure diffusion and driven by pressure fronts inside the climbing system? And it's actually when is that coming up with the advection of magma?
Yeah. Well, the evidence, so the evidence that really that case is that clearly there is an arrival spot. There is clearly a volatile degassing. Then, I mean, what is pushing what is, that's, and the relation between the two, that's, we still cannot resolve that.
Because also then the magma shape, what else is interacting with magma?
Of course, yeah.
I mean, the data about UPA, I think, is, I mean, strongly, it's really one of the best study volcanoes to do this sort of work.
Yeah.
And when I look at the combination of what Chiara is doing and what UPA is measuring in the gas, you start to see the large trends you were showing in CO2. It's really interesting because then they went back to that data.
Yeah,
Basically, you could have said months before that something was about to happen.
exactly. That's why they realized that there was something going on, and you can see from the time scale that actually you have something. Yes, I mean it's the normal activity, probably it's the normal activity of Stromboli, but since we don't have really data on how frequent you have the charge, is that really the normal activity or is something that is going on? The other thing is that when Ayuba looked at the 2019 from the last data, he kind of said that there was like two different mechanisms. One, so for the first paroxysm, it was a bottom-up, but the other one was a top-down, so more driven by the gap. But actually, I mean, the time scale seems to say actually not, because we don't really find any overlap of time scale between the 20th of August and 3rd of July. So it seems there are two different, really signaling two different magma recharge. There is no overlapping of time scale whatsoever. This might be a chance because they were not erupted, but also if we think that the mechanism of paroxysm is like mostly shooting through, why they were not picking up other crystals? Why did the 20th of August pick up other crystals that were kind of slightly wrong?
Perhaps the last one. Yep.
Just some very nice maps of the equipment in nickel, and you said you were not correlated. Just too much because you have an enrichment equipment that you don't see in nickel. Like, I think I missed why. What's the explanation? What do you think that is?
Okay, so okay, it's gone. Sorry. Oops.
It's doing this with the low Y.
I have no idea. Here. Okay, so yes. So basically, you can see here we have the chromium and nickel that are correlated. In this case, they are not. So in this case, I don't believe that. Well, the indication is that they are not due to the mafic recharge, because chromium and nickel they really go, and the LP magma has a strong signal of magnesium rich, chromium rich, and nickel rich, and it's more like that these crystals they grow spinning basically. And the growth is kind of, and the spinning, so the combination between the growth and the spinning does not allow to re-equilibrate. And so you have the mafic recharges start to spin all the crystal, and they grow in this spinning system and they cannot re-equilibrate, so the chromosomes cannot keep up, which is the only, the only one that is, well, it's not the only one, because that's also that there is, you can see this in aluminium, in titanium, in other elements. And there are some experiments from the Fiore that they show that the growing in spinning in a convective regime, you really have a kinetic effect due to this, and this crazy wind.
The ground is not making mercury rate with the mechanics.
The nickel was actually, because the nickel was low in the atoms, yeah. But you have other elements that they show the same.